The topic of this lecture is Important Theorem, Part 4 of Complex Analysis. In this lecture, we'll cover theorem number 1 and theorem number 2. That is, two theorems we are going to cover in this lecture. So let us see the first theorem. It says that let f function f is analytic at a point z naught. That is our first supposition. And f has a 0 of order m at z naught. This will happen, that is, if and only if there is a function g which is analytic and non-zero at z naught such that fz is equal to in bracket z minus z naught to the power m into gz. So if this happens, then f will have a derivative at z naught of power m, or conversely, if f has 0 of order m, then fz can be written in this way. So let us see the proof. As f and g are analytic at z naught, so f and g have Taylor series X representation in power of z minus z naught, which is valid throughout a neighborhood z minus z naught less than epsilon of z naught. Now, since Gz is analytic at z naught, it has a Taylor series representation given by Gz is equal to Gz naught plus G dash z naught divided by factorial 1 z minus z naught plus G double dash z naught divided by factorial 2 z minus z naught square, and so on. Then expression 1 becomes fz is equal to Gz naught z minus z naught to the power m G dash z naught divided by factorial 1 z minus z naught to the power m plus 1, and G double dash z naught divided by factorial 2 z minus z naught to the power m plus 2. That is, this expression, because of this, becomes this expression when z minus z naught is less than epsilon. Since this is actually nothing but a Taylor series expansion of fz, it follows that by putting the value z naught, z is equal to z naught over here, we get fz naught, which is equal to 0. Then finding the derivative of this one time and putting z is equal to 0, we get f dash z naught is equal to 0, and so on up to f m minus 1th derivative at z0, we get the value 0 from this expression by doing the successive differentiation. And finally, when we find the mth derivative of this expression, we get the value, and we put value z is equal to z naught because of this first expression. And when we find the mth derivative, we get this is factorial m into g z naught, which is not equal to 0. Therefore, by definition, because all these values are equal to 0 and the mth derivative of f at z naught is not equal to 0, by definition z naught is a 0 of order m of f. Now let us see the converse part. Suppose f is analytic at z naught and f has a 0 of order m at z is equal to z naught. So by definition, f at z naught, f dash at z naught, f double dash at z naught, and f m minus 1 at z naught, all the value will have a value 0. And the mth derivative of f at z naught is not equal to 0. And there is a Taylor series of fz in some neighborhood z minus z naught less than epsilon, given by fz is equal to n is equal to m to infinity fn z naught divided by factorial n z minus z naught to the power n. This is because all these derivatives are 0. Now expanding this, we can write this is a z minus z naught to the power m, and in bracket mth derivative of f at z naught divided by factorial m, m plus 1th derivative of f at z naught divided by m plus 1 factorial into z minus z naught, and so on. So this expression, and this can be written as z minus z naught to the power m, which is outside this, and whatever is in this box bracket, we are denoting this by gz. Now the convergence of this last series, because this is convergent, this series is convergent because fz is analytic. So the convergence of this last series when z minus z naught is less than epsilon ensures that G is analytic in this neighborhood and in particular at z naught. Moreover, Gz naught, which is equal to mth derivative of f at z naught divided by factorial m, is not equal to 0 because of this supposition. So we are successful in writing fz as a z minus z naught to the power m into gz. So this completes the proof. Now let us see the next theorem. This says that if a function f is analytic everywhere in a finite plane except for a finite number of singular points interior to a positively oriented simple closed contour C, then the integral of fz around C can be expressed as integration of over C of fz dz is equal to 2 pi I into residue at z is equal to 0 of this function, that is 1 upon z square f at 1 by z. Now let us see the proof. So suppose that a function f is analytic throughout the finite plane except for a finite number of singular points interior to a positively oriented simple closed contour C. So this is our contour C, and inside this, these are all the singularities. Let R1 greater than 0 such that C lies inside the circle mod Z is equal to R1. So this is the circle R1 inside which the curve C lies. The function f is analytic throughout the domain R1 less than mod z less than infinity. This is very clear. And the point at infinity is called isolated singular point of f. Now let C naught denote a circle mod z is equal to R naught oriented in the clockwise direction when R naught is greater than R1. So this is the expression. Note that here inner circle is positively oriented and the C is positively oriented and C naught is in clockwise direction, so it is negatively oriented, we can say. Then the residue of f at infinity is defined by the equation integration of fz over c naught dz is 2 pi I residue at z is equal to infinity of fz. The point of infinity is on left side of circle C naught. Since f is analytic throughout the closed region bounded by C and C naught, the principle of deformation of path, we have integration of fz over C is same as integration of fz dz over minus C naught, and this is same as minus of fz dz over integration of fz dz over C naught. Therefore, integration of fz over C, this will be equal to minus 2 pi I residue at z is equal to infinity of fz. Now to find this residue, we write the Lorentz series fz in this way, n is equal to minus infinity to infinity Cn z to the power n, which is valid in this region where Cn is given by 1 upon 2 pi I integration of fz dz divided by z to the power n plus 1 over minus C naught circle. Now replacing z by 1 by z in this expression number 2 here and then multiplying throughout the result by 1 upon z square, we see that this expression is 1 upon z square f1 by z naught is equal to summation n is equal to minus infinity to infinity Cn z to the power minus n minus 2. And the value of coefficient C minus 1, which will be residue of this function at z naught, that will be residue. Now putting n is equal to 1 in the expression number 3, which is expression number 3, this is expression number 3. Here we put n is equal to minus 1 we get c minus 1 is 1 upon 2 pi I integration of fz dz over minus c naught. And this gives c minus 1 is minus 1 upon 2 pi I integration over c naught of fz dz. From this we obtain that integration of fz over c naught is equal to minus 2 pi I c minus 1, and the value of c minus 1 will write. So it is minus 2 pi I residue at z is equal to 0, 1 upon z square into f1 by z. Because recall from the last slide, the value of c minus 1 is equal to this. So because of this we obtained this expression. Now since f is analytic in the closed region bounded by c and c naught, so using the principle of deformation of path, we have integration over c of fz dz, which is equal to minus integration fz dz over c naught, that is equal to 2 pi I residue at z is equal to 0 of the expression 1 upon z square f1 by z square. This we obtain from this one. So thank you very much. You can find the link of this PPT in the description box. Thank you.